We'll move on to the third type of relation access algorithms, which is hash-based algorithms or hash-based relation access. The idea is simple. We're going to read the relation page by page or block by block, and then take each tuple in a block and hash it. The hashing data structure here could either be an extensible or a linear hash table if the memory cannot hold the content of the table. Now, the rationale is like this. All tuples that are similar should hash to the same bucket. Okay? Now, what this means, if I use the same hashing mechanism and I see the same value and I am building two hash tables, the same value should fall in the same bucket in the two hash tables. So really it boils down to comparing the buckets to do the operation I'm interested in. Okay? Let me show an implementation of this for, again, duplicate elimination. So I have a relation and I would like to eliminate duplicates from a specific column. So we have seen a version where we used sorting. Here we're going to use hashing. I'm going to again read the relation because I need to build a hash table. I'm going to read the relation block by block or page by page. I will retrieve a row. I will go to the column I am doing duplicate elimination on. I will get the value and hash it or insert it into a hash table, regardless of whether this is extensible or linear or an in-memory hash table. I will just insert it into a hash table. Now, when I'm done with this process, all the duplicates that I have came across, because it's the same value, it will hash to the same bucket. If it's an in-memory hash table, I'm using an array internally inside this hash table, it will exist in the same bucket. If it's an extensible or a linear hash table, it will still fall in the same bucket because we discussed when I explained extensible and linear hash table, we said that we deal with duplicates by placing them in the same bucket. So what I'm going to do is afterwards, we just go to the bucket and we will find in the bucket the duplicates together. So I will eliminate all of them except one. And then I print the content of the buckets after doing this elimination. So the nice thing is, this is one pass to read the whole relation. And then if the hash table fits in memory, whatever happens afterwards will also fit in memory because this involves deleting entries from the hash table. So if it was too big at the beginning, now it's becoming smaller because I've just deleted all the buckets. And then while they are still in memory, I go and visit all the buckets, one bucket after the other, to do the elimination and then do the printing. If it doesn't fit in memory, the hash table, then I'm forced to use extensible or linear hash table. But again, it's going to be an exercise of visiting the buckets, deleting the duplicates, and then printing out the remaining content.
Now, another example of a hash-based algorithm is the hash join, which is an algorithm used to join two tables on a common column. In this example, we are trying to join two tables, R and S. R has two columns X and Y, and S has two columns Y and Z. Obviously, Y is the common column. Now recall that the join operation means you would like to include in the result set all rows where the Y value is the same in R and S. So, as we've discussed in the previous lecture, the way to think of a join implementation-wise is we are grabbing a single value from the Y column, say from the R table, and go and look for it in the S.Y. Now, the way the hash join algorithm proceeds, just like all hash-based relation access algorithms work, we're going to build a hash table. So I will grab r.y, all the values in r.y, and I will insert them into a hash table. And next I will grab or extract all the values in s.y and insert them into a second hash table. What I'm going to do next, I will compare the buckets, bucket to bucket, between the two hash tables. So I will go to bucket 0 that I have built in hash table in the hash table for r.y, and I will compare its content with bucket 0 in the hash table that I have built using s.y. And then I compare bucket 1 in the first hash table to bucket 1 in the second hash table, and then bucket 2 in the r.y hash table to bucket 2 in the s.y hash table. Now, when I'm comparing corresponding buckets, I am looking for entries that are common between the two buckets. So obviously this will involve linear scanning of these buckets, but you could think of this as an O of k operation, and it's still fairly fast. It's not O of n for sure. The hashing itself of the value and placing it is an O of 1 operation, but comparing the buckets will require some processing, but we consider it as an in-memory activity, so it is not a major concern to us. The key to understanding this is that if we use the same hash function for the two hash tables, the two separate hash tables we're going to build, one for r.y and another one for s.y, the same value will hash to the same bucket. So if I see in r.y the value 50, and I pass it to the hash function, and I get as an output from the hashing function the number 7, which means I'm going to put this value 50 in bucket number 7. If in s.y there is 50, I use the same hash function, so I'm going to also get 7. So when I'm inserting it in the second hash table that I built on s.y, the value 50 will also go to bucket number 7. So by comparing corresponding buckets, I can easily find entries that are common between r.y and s.y. And instead of trying to search in the whole of S for 50, I will find it in bucket 7 in both hash tables. So comparing the buckets is an efficient way to do any SQL function that you'll be interested to do. This doesn't just include joining. What I'm describing here is the hash join algorithm. We could think of corresponding algorithms for calculating the minimum or the maximum or counting values. Any kind of operation where we are interested in browsing through the data to do some kind of computation using a hash-based approach will be faster than a linear scanning of the values. And notice that we are using a one-pass algorithm here. Reading all of R and building the hash table is one pass. Reading all of S and building the hash table is one pass. And even if we are using a secondary storage hash table, like an extensible or linear hash table, we will still do one pass on the buckets. We don't need to go back and forth. We will compare bucket 0 to bucket 0, bucket 1 to bucket 1, and this goes on from the first bucket all the way till the last bucket. The fourth type of relation access algorithm, as we've discussed, are index-based algorithms. Just as the name implies, what we are doing here, we're using an index. We've seen this notion that database engines are so sophisticated that to access a relation to satisfy a specific SQL statement that you've passed, it can do a number of things, and one of them is to build an index on the fly. We've seen it with sort-based scanning, where it was doing an additional activity with hash-based indexing, the one we were just talking about. And obviously, it's going to be the same for using any kind of index that it might find more efficient to create and use to answer a query and then delete afterwards. So even though hash-based relation access algorithms are a type of index-based algorithms, they are usually dealt with separately and classified separately because of the good performance of hash-based techniques. You're talking about an O of 1 operation. But it doesn't have to be hash-based all the time. Sometimes the database engine will create an index, not a hash-based one, but another type of index, for example, a B plus tree or an R tree, depending on the query that you are passing to the engine. The idea here is that using an index, even though it's created on the fly and there is some time spent creating the index just to answer a query, the idea is that this is much better from the database engine perspective than doing a linear scan. Okay? Now, the one technique I will show you, again, just like we've discussed before, for the four types of relation access algorithms, we have, for every type, many implementations to support all the SQL functions and operators you have in SQL. I will describe to you here one specific type of an index-based algorithm, which is a type of a join, an index join algorithm. Specifically, it's called a zigzag join. A database engine would do zigzag join if you have created, or it decides to create, two B plus trees to answer a join query. The example we're looking at here are two relations R and S again, and the common column is Y. Now, what the database engine will do is it will create an index on R.Y, a B plus tree on R.Y, and create another B plus tree, a separate one, on S.Y. The way it used them together, the two B plus trees, is quite unique. That's why it was given the name zigzag join, and it's considered a special kind of index handling or index usage. What actually happens is that the database engine would alternate between the two B plus trees to try as quickly as possible to isolate the segment at the leaf level between the two trees that has the answer to the join query. So let me here try to plot some numbers so you understand what I'm referring to. My computer just went for a while and came back. Let's say this is my first tree, and this is another tree. if the values here go from 5 till 25 at the leaf level, and if the values here go from 1 till 15, what is the range that I should be interested in to answer the join? Remember, we're looking for common values between r.y and s.y. So since 1 does not exist here, it's not interesting. The interesting stuff will start from 5, because this tree on the right starts from 5. Now, are we interested to go all the way till 25? And the answer is no, because this tree ends at 15. So really, our answer will lie between 5 and 15. Now, looking at just one of the two B plus trees, one at a time, is not sufficient to find this answer, 5 to 15. What we have to do is to alternate between the leaves of the two B plus trees to identify the segment of interest. And this is what I try to highlight here with this illustration, that we're going up and down. Here the tree is reversed, so this is the root here, and this is the leaf, while this is the root on this side. So what we are doing is we're alternating back and forth between the leaves of the two trees to identify this segment. And once we identify it, we will just focus on this segment to find the values that appear in both B plus trees. Now, how do we go actually about doing that? I will start by comparing the two minimums of the two B plus trees. So I will go from the root all the way till the bottom. And then I will find which one is larger. The 5 is bigger than the 1. The 5 is here, so I will search here for the 5, going down and from the root to this one. Okay? Now I have here a trivial example, and consequently I don't want you to think that, okay, why don't I follow the next pointer? Because this value, the 5 that appears to be here, a 5, could be way inside the tree. So I don't want to load all these nodes to find the value that this one starts with. I will just go and search for it, starting from the root, in a nice log n performance. Now, I will also compare the maximum here and the maximum here, and since this is 15, I will go here and look for the 15 until I find it, or I find something or value that is just greater than it. And this will be the interesting segment to me, because it will hold my answer, which is the common values between r.y and s.y. And this is another example describing the same algorithm that we were just discussing. Obviously here, if I ask you what is the interesting range, well, notice that this tree ends at 23, so I don't need to check beyond 23. And since 23 does not appear in the top 3, I'm really stopping here at 25. Everything to the right here is of no interest to me. Now, as a minimum, this is 1 and this is 2, so anyway, I will start from the left, starting from the 2 here, since I have a 2 here and there is no 1 here. It's the same algorithm that we just described. Now, to summarize, there are several techniques to access a relation content to perform a specific SQL operation. Linear access methods, sort-based methods, hash-based methods, and index-based methods. And as I mentioned before, all of these guys are implemented for every SQL function and operator that you know of inside the database engine. And the question becomes, if you wrote or if you write a good SQL, you'll pick one of the nice ones or the better ones, which are typically hash-based indices or hash-based methods or index-based methods. If you just write the SQL without thinking of all of this, then you run into a problem of having the database engine using a linear access method, which is the worst of all of them in many situations. So to summarize, to build a physical query plan, you got to implement, if you're building your own database engine, I think you got a taste of it in project 1, but you were just beginning to do that. If you get too excited and you decide to build your own database engine, then you will have to support physical plans, and that means implementing operators and implementing all data access methods, as we described already. Now, we have been describing what is a physical plan. We're now going to focus on how to actually optimize a physical plan, how to decide on which physical plan to choose among the many options you have, including the data access or the relation access methods, which one to pick. Or in other words, when you actually try to trace the execution of a SQL statement inside a database engine, which you're going to do, inshallah, in your project 2, how does the database engine decide which access method to use? The main criteria that is used by database engines is to count the I/O that it's going to do to execute a specific physical plan. We mean by an I/O how many times the hard disk is going to be moved, or specifically the hard disk arm is going to be moved to read part of a table, basically a page, if you store a page in a cylinder. So it's not going to actually run it and see how many times it did it. What it's going to do is it's going to do something similar to what we have seen in lecture 7. It's going to estimate the number of input-output operations, or simply the estimation of how many times the hard disk arm moves. Now, why is this used as the measure? Why are we concerned about the number of times the hard disk arm moves? Because this is the slowest activity you can do while you're actually trying to access the data. The problem with hard disks is that, at least with magnetic hard disks, is that it's a mechanical device, or specifically it's an electromechanical device. Because of friction, because of the mechanical aspect, it is really slow compared to electronics. So we try to focus on the bottleneck, basically, which is the hard disk movement, or the hard disk arm movement. And that will become our concern. So we will compare physical plans based on the number of IOs, which is the number of hard disk movement or arm movement. And we'll pick the one that moves the hard disk the smallest number of times. Now let's go back to this notion of hard disk arm. If you remember, I discussed this in the previous, in the first lecture. This is how a hard disk looks like if you open one of yours, and if you try to understand what are you looking at, this part that I'm labeling is actually called the arm, and this is this part. Now, the hard disk consists of platters, as probably you remember from your quiz, and the platter has two sides. The platter has tracks. They are divided into sectors, and this head that is labeled in black reads from a sector. The worst mechanical thing that could happen here is the movement back and forth of this arm. Why? Because we have many sectors along this surface. So this guy moves towards the center, towards the spindle, and back. Every movement is one I/O. Every time we move and stop, that's one I/O. Now, what we're trying to do is we would like to minimize this movement. And we've described early on a technique to actually minimize this movement by storing the page of a table on sectors that lie on the same vertical axis. So I'm not good in drawing straight lines, but if this is a straight line, all the sectors that are on this straight line will be a cylinder. We'll make a cylinder. That's what you see actually here. Okay, and we are going to store a page this way. So our golden metric is the I/O. Now, we went into a discussion at least 2 times in the course, and I will remind you with this again, that ideally I want to store a page in the same cylinder. And this is really possible in one scenario if you have your own file system. But if you don't have your own file system, you have no control on other programs that are running, that are accessing the file system at the same time you're accessing it, and writing information all over the hard disk. So if you store a page in a cylinder, with one I/O you can retrieve a page. But if you are not able to guarantee that the page is stored in a cylinder, then you could spend multiple I/Os to read one page. So this is what we're going to do to estimate the number of I/Os. We will be concerned with how many pages or how many blocks a relation is stored in. And we will be interested in some point to talk about how many tuples at max I can put in a page or a block. What also we're going to be interested in, how many memory blocks or pages are available for us. The thing is, inside the database engine, SQL statements arrive at the same time from different parties or different applications or different clients. If you think of the database engine behind Amazon or Sue or Jumia, at any point in time there could be many people buying different stuff. Every time someone buys something, that involves an insert statement into the table, say the orders table. So the way things run inside the database engine, when a SQL arrives, it's going to be put in a container, which we are going to describe in detail later on, called a transaction, and a number of memory pages are allocated to it. And this SQL cannot use more than that, those memory slots. So I'm referring to that as M. It could be 3, it could be 5, could be 100, depends on the configuration of the server, depends on many things. But the point is, you don't have open access to all the memory locations, even though there might be nothing running beside your request, your SQL, and you have a very low load on the database engine. Database engines do not open, the door for abuse by the SQL writer. So your SQL will run using or utilizing a small number of memory pages, and we refer that to M as M. So this is how we are going to compute things. Now the other thing we also need to highlight here is this notion of ordered versus contiguous. Now let's go from left to right here. On the left you see those 2 pages that belongs to the same table. The values are sorted. That's why I say this is ordered. 10, 15, 17, 19, 35, 37, and so on. If I say that this relation is also contiguous, this means these rows the three I'm just labeling, putting an X on them, are stored in a cylinder. So I will read this page. Let me just put a circle around it. I will read all of this in one I/O because they are stored in a cylinder, as we described before. So this is ordered and contiguous. Now over here, these guys, I can have another variation where, as you see in the middle here, if I say this is unordered and contiguous, this means the entries in this specific column I'm interested in are not sorted. So this table must be sorted according to some other column. But if I say it's contiguous, this means in one I/O, I can read one page because all of these three rows are stored in a page, and that is stored on a single cylinder. So there's a difference, between saying it's unordered versus being contiguous. They're two separate issues. Okay? Now I have a third scenario, which is the data or the values in the column I'm interested in are not ordered, and the relation is not contiguous, which means the entries, the rows, are not stored in the same cylinder. They could be partly stored in a cylinder and partly on some other cylinder. So the general case is that when I do an I/O, I will be reading one row. So to read these 6 rows, I will spend 6 I/Os. The first I/O to read 35, the second I/O to read 19, the third I/O to read 37, and then the 15, the 10, and the 17. Obviously, this is a worst case scenario, not a general case. It's a worst case scenario, but we will treat it as always as the worst case, in the sense that if I say it's non-contiguous, then I will think of it as the worst case, which means it's completely fragmented. It's not partially fragmented, it's completely fragmented. The number of I/Os is actually the same as the number of rows in the table. Okay? So there are two separate issues, ordered versus contiguous. Obviously, what's of concern to us here is being contiguous versus being non-contiguous. And again, if you don't have access to the file system, direct access to the file system, okay? Which means you create your own partition, the database engine creates its own partition and prevents, consequently, other applications from writing to this partition. And the database engine comes with its own file system, so it has control on storing information inside a cylinder. Then the general case is that is going to be the worst case, which is that it is non-contiguous. So let's try to think of estimates for doing a join on two tables, R1 and R2, obviously with some common attribute. If the number of rows in R1, TR1 is 10,000, the number of rows in R2 is 5,000, obviously the size of, actually no, it's not obvious, it's just an assumption here that the size of R1 is equal to the size of R2, which is that it takes 1/10 of a block. In other words, I can store 10 rows or 10 tuples in a page or in a block. Okay? So I have 10,000 rows in R1, and I will store 10 rows in a page. That's what the F means. Now, that means I will have 10,000 divided by 10, I will have 1,000 pages for R1. So I can just write it here. This, I will have 1,000 pages. Now over here, I will have 500 pages. Now, I am giving the following, that to run this join, this SQL join, my M is 101 blocks. So I have 101 pages in memory available for me to use whatever way I like to actually perform this join. But obviously this is way less than what I want, because I'm saying here I have 10,000 rows and 1,000 pages, and I have 500 pages in R2, and I just got 101 pages that is available to me. Okay? So one thing I need to mention here is that we're not going to be concerned when it comes to computing the I/O with the writing of the result set to disk. Well, is it written to disk? It depends. It depends. It depends how we're doing the join, the relation access method, and how much memory is available to us, and how big is the result set. So I'm just going to ignore writing it to disk. Okay. Now we're also ignoring other operating system related issues, like for example that the operating system decides to kick some of our 101 available pages in memory and move them to virtual memory, so they're now on disk. So actually it's expensive to access one of those pages, because when we try to write, we're going to spend an I/O to write it to disk while we think it's actually in memory. I'm going to ignore all of that because this is not under our control. It's an operating system issue. So if we just look at the join as a very popular operation in the SQL world, we have 4 options. So when a database engine gets a SQL statement that has a join, it has 4 options. To use either iteration join, which is a type of sequential scan, or a merge join, or an index join, or a hash join, the ones we described earlier. So what we're going to do is we're going to compute the cost for every one of them, for each one of them, and figure out which one is the optimal one by having the smallest number of IOs. That's how it's actually done inside a database engine. So let's look at iteration join. So this is simple linear scanning to do a join. I'm going to go to R1, and for every row or in R1, I will go and loop on S to find a match for the common column, which is C, R1.C, with S.C. So this is like a pair of nested loops. It will literally be written like this. It's the outside loop is iterating on R1, the inside loop for every iteration from the outside one, the inside one will iterate on all of R2. Doing this check, R1.C with S1.C. Since this statement is inside the for loop, this will be executed as many times as there are rows in R2 with a single value from R1, which is R.C, and then that will be repeated over and over again. So if this has 5 rows, this has 10 rows, this statement will be executed 50 times. Okay? Now obviously this is expensive, as you should be looking at this and saying, like, if this has 1,000,000 rows and this has 500,000 rows, that's 1,000,000 by 500,000. That's like a ridiculous type of computation. Okay? Now, what we just did is correct from a logical point of view, but we are missing something. We're not using the memory at all. Okay? That's something we're missing. We have 101 blocks which we could use to cache parts of the table. So let's see it step by step. Now, let's first look at the case where the relation is not contiguous. Okay? The two relations, R1 and R2, are not contiguous, which means I will spend 1 IO to read 1 row. Okay? Now, how does this compute? For each R1 row, I will read that row, so I will spend 1 IO reading a row from R1, and I will read all of R2. That's the logic we were just looking at, the nested for loops. I will read 1 from R1 and go and read all of R2. Okay? Many times I'm going to do this, as many times as there are R1. So it's reading 1 from R1 and then reading all of R2. So it's 1 plus 5,000, 1 IO plus 5,000 IOs, because again the relations are not contiguous. So I will spend 1 IO per row. So 5,000 IO for R2 1 IO for R1, and I will do the match on the 1000 against the 5000. So let's say I got from R1 the value 20. So I will go and read all those, and I got that using 1 IO. So I will go and read all of R2, which has 5000 rows. Each row costs 1 IO, so that's 5000 IOs. So what I just did, I just spent 5001 IOs. How many times I'm going to do this? I'm going to do this 10,000 times, because R1 has 10,000 rows. And I'm doing it for every row. And every row costs me an IO. So the total is this ridiculous number of IOs. Now, is this good? No, this is really bad. You're talking about moving the hard disk around 50 million times. Okay? What we're missing here, as I mentioned, we're not using the blocks. If we just use some of these guys, these 101 blocks, we will drop this number significantly. Okay? So, let's see how we do better. We're going to use the memory. This is what I'm going to do. I'm going to read 100 blocks of R1 and keep it there. And by the way, this is a little bit naive, but just to show the point. I have 101 memory blocks. Okay? This is what I told. I have 101 memory blocks. I will read 101 pages or blocks from R1 and put it in memory and keep it there in memory. And then I will read all of R2 one block at a time and put it in the remaining block. Because I have 101, I used 100, so one is remaining. So I will use the only remaining one for R2. Okay? This will be our strategy. To cache basically the blocks of R1 so that we can repeatedly compare their content against R2. Okay? Now, so this is again what I'm saying here. I will describe the part I am caching from R1 as a chunk. So I will read a chunk, and the chunk here is going to be 1000 IOs, because the 1000 IOs will fill for me 100 pages, since a page takes 10 rows. And since this is not contiguous, so 1 IO equal to 1 row, or 1 IO enables me to read 1 row. So if I spend 1000 IOs, I am going to spend 1000 IOs to read 1000 rows from R1 and put them permanently in memory until I don't need them anymore. And then I'm going to go and read all of R2 row by row, spending 1 IO for every row, and since R2 has 5000 rows, I will spend 5000 IOs. So in total I will spend 6000 IOs. But what is this enabling me to do? Is to match 1000 IOs, sorry, 1000 rows from R1 with all of R2. But R1 has 10,000 rows. Okay? So I will actually do that 10 times. The 6000 is for 1/10 of, or for matching 1/10 of R1 with all of R2. I still have the other 9/10. So the way to compute it is, this is the cost of a chunk, and I'm going to figure out how many chunks I have. A chunk has 1000 rows, and since I have 10,000 rows, so I'm going to divide the 10,000 by 1000 to get a 10. So I really have 10 chunks. Multiplied by 6,000, so now this will cost me 60,000 IOs instead of 50 million. Okay? Now, the question is, can we do better? And the answer obviously is yes. We can do better if we reverse the relation, or if we swap the relation we are caching. So let's do that. I will cache a chunk of R2 instead of R1, the smaller one, and I will keep that in memory until that chunk I don't need it anymore, and I will get rid of it by overwriting it within the second chunk. So again, this is not contiguous, so I will spend 1 IO per row. So I will fill in the 100 pages. Again, I have 101 memory pages. I will use 100 of them to cache a chunk of R2. The 100 pages will have 1000 rows, since every page holds 10 rows. So I will spend 1000 IOs to fill a chunk. And then I will use the remaining page in memory available for me, the only one that is free, to read R1 page by page. R1 has 10,000 rows. I will pay 10,000 IOs for that. In total, to process a chunk of R2, I will spend 11,000 IOs. So this becomes this part. Now, I need to multiply this by how many times I'm going to do it. And this is related to the size of the chunk. Well, in total, R2 has 5,000 rows. The chunk is 1,000. This means I have 5 chunks. So the cost of one chunk is this much, 11,000 IOs. So now we are standing at 55,000 IOs instead of 60 IOs as in the previous slide. So we're doing even a little bit better. What if the relation is contiguous? Contiguous is a big advantage because that means I will spend one IO to read a page, not a row. So let's do the recalculations or the calculations again, but thinking now that one IO means a page. So I will just apply the last strategy we've seen, which is to chunk the small relation of the two. Now, when I put in a chunk of R2, I will waste or I will spend 100 IOs. Every IO reads me a page because now a page is stored in a cylinder. And that means these guys will go, as I mentioned before, this will go into 100 pages in memory. 100 pages in memory. I have remaining, actually this is not correct. I have remaining 1. So the 1 I will allocate it to R1. Now I will read all of R1 pages, page by page, and put this page inside the available memory slot that is remaining for me. And since R1 has 1,000 pages, I will spend 1,000 IOs to read the 1,000 pages, page by page, in order to do the comparison. Remember, like we're doing all this because I would like to compare R2.c with R1.c. Okay? So I will load a page of R1 into the available memory slot using 1 IO, and then I will go and match R2.c chunk or R2.c in the chunk with R1.c now in memory. Okay? If you'd like to visualize it, I have here now 100 pages. Okay? I'm really bad at drawing. From 1 to 100. All of these belong to R2. And I have one only page from R1. Once I have this set up, I will match the rows here with R1, and then the rows in this page with R1, all the way till the last page in the chunk with R1. And then when I'm done, I will delete all of these guys, the R2 chunk, and put the next 100 pages. Okay? Now, the thing you have to understand is, with one chunk of R2, which is the 100 pages, here in this page, I will read all of the pages in R1 one by one into this slot to do the comparison, and then the next one, and then the next one, and then the next one, all of R1 using a single page. Now, in the case of a contiguous relation, you see how beautiful the performance become. It's a 5,500 IOs instead of 55,000 IOs. Okay? This is why, as I mentioned before, people pay for Oracle. Now, I'm going to stop the lecture today at this point, and we will continue next time with other techniques to perform the join using other relation access methods.